Time, as we experience it, seems constant. We wake up, go about our day, and sleep, all within the confines of what we believe to be a steady, unchanging flow. It's the steady beat to our lives, a rhythm that we rely on to structure our days and nights. Sunrise, sunset, the ticking clock all reinforce this sense of time's unwavering flow. These daily cycles give us a sense of order and predictability. But what if I told you that time isn't as straightforward as we perceive it? What if our understanding of time is just a simplified version of a much more complex reality? What if I said that time is more like a river, its flow changing depending on the surrounding landscape? Just as a river can speed up or slow down, so too can time. Imagine a river, its current swift in some places, languid in others. This variability is akin to how time can behave under different conditions. Similarly, time's passage can be influenced by factors like speed and gravity. The faster you move or the stronger the gravitational field you're in, the more time can stretch or compress. This bending of time's river is what we call time dilation, a concept that sounds like science fiction but is in fact a fundamental aspect of our universe. It's a phenomenon that has been proven through experiments and observations. Hold on to your hats, folks, because we're about to dive into the mind-bending world of Einstein's relativity to understand how time itself can be stretched and squeezed. We'll explore how this concept not only challenges our everyday experiences, but also opens up new possibilities for understanding the cosmos. Albert Einstein, the maestro of modern physics, revolutionized our understanding of time and space with his groundbreaking theory of relativity. This theory fundamentally changed the way we perceive the universe and our place within it. Now, I know relativity might sound intimidating, but bear with me. It's not just a collection of complex equations, it's a beautiful, intuitive concept that reshapes our view of reality. Imagine the universe as a giant trampoline, a vast, flexible fabric stretching out in all directions. When you place a bowling ball, representing a massive object like the sun, on the trampoline, it creates a dip, a curvature in the fabric. This dip is a visual metaphor for how massive objects distort space-time. This curvature is what we perceive as gravity. It's not just an invisible force pulling objects together, it's the very shape of space-time itself. Roll a marble across the trampoline and its path will curve as it passes near the bowling ball. This is similar to how planets and other celestial bodies move through the curved space-time around stars. Einstein's theory tells us that massive objects like stars and planets warp the fabric of space-time, much like the bowling ball on the trampoline. This warping is a fundamental aspect of how gravity operates in our universe. This warping affects not only how objects move through space, but also how time itself flows. Near massive objects, time actually slows down, a phenomenon known as time dilation. This means that the closer you are to a massive object, the slower time moves for you compared to someone further away. Let's talk about the International Space Station, or ISS, a marvel of engineering that orbits our planet at an astonishing speed of about 17,500 miles per hour. That's fast. To put that into perspective, it circles the Earth approximately every 90 minutes. But the ISS isn't just zooming around our planet, it's also experiencing a slightly weaker gravitational pull than we do down here on Earth's surface. Remember the trampoline analogy? The ISS is farther away from the bowling ball of Earth, so the curvature of space-time is less pronounced. These two factors, the ISS's speed and its distance from Earth, combine to create a fascinating playground for exploring the effects of time dilation. Here's where the mind-bending part kicks in. Because of its speed and gravitational environment, time passes ever so slightly slower for astronauts aboard the ISS compared to us Earthbound folks. We're talking about fractions of a second over a 6-month mission, but measurable nonetheless. Think of it this way. Astronauts on the ISS are essentially time travelers, albeit on a very small scale. They age a tiny bit slower than they would back on Earth. It's not enough to make them look younger, but it's a real phenomenon that highlights the malleability of time. Now, you might be wondering, how do we know this is actually happening? Well, thankfully, we have some incredibly precise timekeeping devices to help us out. Section 5. Atomic clocks, keeping cosmic time. Atomic clocks are the unsung heroes of modern physics, measuring time with astonishing accuracy. These devices operate on the principles of quantum mechanics, using the vibrations of atoms to keep time. These timekeeping marvels are so precise that they wouldn't lose or gain a second in millions of years. This level of precision is crucial for various applications, from GPS navigation to synchronizing financial transactions. Scientists have used atomic clocks to directly measure the time dilation experienced by astronauts on the ISS. This phenomenon occurs because the speed at which an object moves and the gravitational field it is in can affect the passage of time. By comparing the ticking of atomic clocks on the ISS to identical clocks on Earth, researchers have confirmed that time does indeed move slightly slower for the astronauts. This is due to the weaker gravitational field and higher velocity of the ISS compared to the Earth's surface. These experiments provide concrete evidence for Einstein's theory of relativity, showing that it's not just a theoretical concept, but a real phenomenon that governs the universe. The ability to measure such minute differences in time has opened up new avenues for scientific research. But the implications of time dilation go far beyond just proving Einstein right. Understanding how time works in different environments can help us develop better technologies and prepare for long-duration space missions. It has profound consequences for the future of space exploration. As we plan missions to Mars and beyond, knowing how time dilation affects astronauts will be crucial for mission planning and ensuring the well-being of space travelers. Section 6. The future of space travel time twists ahead. As we venture further into the cosmos, the effects of time dilation will become increasingly significant. Imagine a future mission to a distant star system light years away from Earth. Traveling at speeds approaching the speed of light, astronauts would experience time dilation on a much grander scale. Years could pass for the astronauts while decades or even centuries pass back on Earth. It's a mind-boggling concept, but one that we need to consider as we push the boundaries of human exploration. Time dilation isn't just a scientific curiosity, it's a fundamental aspect of the universe that will shape the future of space travel and our understanding of time itself. Section 7. The expanding universe of knowledge. Time dilation is a compelling example of how scientific exploration continually reshapes our understanding of the universe. What we once thought was constant and unchanging, we now know to be fluid and relative. This realization opens up a universe of possibilities and challenges our perceptions of reality. The study of time dilation has not only confirmed Einstein's theory of relativity, but it has also paved the way for groundbreaking technologies like GPS navigation, which relies on the precise timekeeping of atomic clocks in orbit. As we delve deeper into the mysteries of the cosmos, we're likely to encounter even more mind-bending phenomena that challenge our preconceived notions. Section 8. Time dilation beyond the ISS. Time dilation isn't just limited to astronauts orbiting Earth. It happens everywhere, all the time, even in our daily lives. The effect is just incredibly small at the speeds and gravitational fields we experience on Earth. For example, technically, time moves slightly slower at sea level than it does on top of a mountain, because gravity is slightly stronger closer to Earth's center. These differences are minuscule, but they highlight the fact that time dilation is an inherent part of the fabric of the universe, not just a bizarre quirk of extreme conditions. Section 9. Time travel. Fact or fiction? Time dilation often sparks conversations about the possibility of time travel, a staple of science fiction that captures our imaginations. While the concept of time travel is tantalizing, it remains firmly in the realm of speculation. Einstein's theory of relativity does suggest that time travel might be theoretically possible under certain extreme circumstances, such as traveling through wormholes, hypothetical tunnels that connect different points in space-time. However, we are far from understanding the complexities of space-time well enough to manipulate it for time travel. For now, time travel remains a captivating concept for science fiction writers and dreamers. Section 10. Conclusion. Time's unrelenting grip. Time dilation is a profound concept that challenges our intuitive understanding of time. It reminds us that the universe is a far stranger and more wonderful place than we often imagine. From the minuscule time warps experienced by astronauts on the ISS to the potential for significant time differences in future interstellar travel, time dilation highlights the interconnectedness of space and time. As we continue to explore the cosmos and unravel the mysteries of the universe, one thing remains certain. Time, in all its warped and wonderful complexity, will continue to shape our journey of discovery.